Maneuvers like these are why we need to be talking about aircraft weight and balance control. Whether you're flying championship aerobatics like Patty Wagstaff, the U.S. Women's Aerobatic Champion, or whether you're flying in a more normal way, or at least more straight and level way, you want to make sure that the aircraft is properly loaded and that the center of gravity is within limits. And you, as the mechanic, have part of the responsibility for that weight and balance control. So the most important reason for aircraft weight and balance control is safety, to make sure that the aircraft and the people in it will fly safely when it is loaded. Now, as far as private aircraft are concerned, FAA regulations do not require that private aircraft be reweighed periodically. They do for commercial operators, but not for private aircraft. Nor do they require that private aircraft be reweighed after any particular alterations. You do calculate a new weight and balance information, but it's normally calculated mathematically rather than by physically reweighing the aircraft. Although there are some times when you do have to physically reweigh an aircraft, and we're going to talk about doing that later on. That would be times like if the weight and balance documentation has been lost, don't have it available anymore, and you've got to start from scratch with a physical weighing of the aircraft. And we'll talk about that in a little bit. You know, many of us over time have experienced weight changes, and that's often true with aircraft as well. The major source of weight change for most aircraft as they age is caused by repairs and alterations. For example, if you replace a standard battery with an approved heavy-duty version or make a minor metal repair, you've probably added some weight. On the other hand, if the avionics shop installs updated radios, they may very well weigh less than the originals. Now, it's likely that there will be some very minor changes in weight due to things like grime, debris in hard-to-reach areas, absorbed moisture in the cabin insulation, or the installation of hardware, safety wire, or maybe layers of paint or primer. But in general, the major source of weight change for most aircraft as they age is caused by repairs and alterations. The empty weight, the operating weight of the aircraft, includes all operating equipment that has a fixed location in the aircraft and is actually installed. That includes the radio equipment, the avionics, instruments, anything that has a fixed location in the aircraft and is actually installed in it is included in the empty weight of an aircraft. Now, is fuel included in the empty weight? Only the fuel that you cannot get out of the aircraft, and that is called unusable fuel. The unusable fuel is included in the empty weight simply because you don't have any choice. When you drain the fuel out of the aircraft to weigh it, you can't get that fuel out. It's the fuel in the lines and in certain parts of the tanks where it just won't drain, and so that will be included in the empty weight of the aircraft. Now, is oil included in the empty weight of the aircraft? It depends on when the aircraft was certificated, but the FAA wants you to know that aircraft certificated under current airworthiness standards, FAR 23, do have the oil included as part of the empty weight. And by the way, that became effective March 1st of 1978. So any aircraft that are certificated under the current standards do include the oil in the empty weight as part of the empty weight, and you don't have to account for it separately. Now, the useful load on an aircraft consists of the crew, the fuel, the passengers, and the cargo. The stuff that you, as the pilot, could load on and go somewhere with, passengers and cargo, yourself as the crew, and the fuel you would put on to help you get there. So useful load is crew, fuel, passengers, and cargo. One way to determine the useful load is the difference between the maximum allowable gross weight of the aircraft and the empty weight. That is the allowable, if you will, useful load. The difference between the maximum allowable gross weight and the empty weight of that particular aircraft. Okay, the maximum weight is the maximum authorized weight of the aircraft and its contents, the loaded weight of the aircraft. And another way to figure that out is to take the empty weight of the aircraft plus the useful load. The empty weight plus the useful load will give you the maximum weight. Now, the maximum weight is determined by the manufacturer of the aircraft. And where you find that maximum weight, you would normally find it in the aircraft specifications or in the type certificate data sheets for that particular aircraft. Now, if you put 3 passengers in your car and fill up the gas tank and the trunk, you wouldn't have any problem at all driving it. Unfortunately, the same is not true with modern aircraft. In fact, the way most modern aircraft are designed, you will exceed the maximum takeoff weight if you fill all the seats, load the maximum baggage, and fill up the fuel tanks. They're deliberately designed that way so that you have choices. You can choose maximum range with fewer occupants or maximum occupants with less range. But if you try and fill everything, you'll almost certainly exceed the maximum takeoff weight. Now, another weight that you need to be familiar with is zero fuel weight. Zero fuel weight is the maximum permissible weight of a loaded aircraft, including passengers, crew, and cargo, but without the fuel. And as you get into larger and larger aircraft, the zero fuel weight becomes important because it's a factor in the stress that the aircraft can take. And the aircraft, you have to be able to figure out or know what the zero fuel weight of a particular aircraft is. And that's the maximum allowable weight of the loaded aircraft, except it doesn't have the fuel, without the fuel. Now let's talk about the datum. The datum is an imaginary vertical line, usually up at the front of the aircraft, from which all the horizontal measurements are taken for balance purposes in figuring the center of gravity on an aircraft. And from the datum line, you measure back to different points in the aircraft. In this case, we've got lines drawn back to the wheels of the aircraft because we're going to be talking about weighing it, but there would also be a distance behind the datum for the different locations in the aircraft where you can put weights in the aircraft. Now, the datum line is usually placed in front of the nose, although not always, and the reason it's usually forward of the nose is because that way all the measurements will be positive numbers, and that contributes to accuracy. If you had the datum line at the firewall, say, then all of the items in front of the datum line would be minus numbers, and you'd have positive numbers to the rear of the datum line, and that would make the calculations a little bit more confusing. So by putting the datum line in front of the nose somewhere, all of these numbers, all of these arms will be positive numbers, and that helps keep things a little bit straighter. So the arm then is the horizontal distance that an item is located from the datum line. And usually it will be after the datum. If the datum is up in front of the nose, it certainly will be, but it's whatever the distance is that an object is from the datum on the aircraft. And the arm's distance is always given, it's always measured in inches, not feet or anything like that. It's always given in inches. Now, sometimes when you're working with aircraft information, you see the term fuselage station numbers. And the term fuselage station numbers identifies the arm distance from the datum, or sometimes from some other point chosen by the manufacturer to measure from. And fuselage station numbers are often used when the manufacturer is identifying the location of parts in the aircraft to tell you where to find different parts in the aircraft. When we're working with actual weight and balance, we usually use the term arm for the distance after the datum, but when you're locating parts, very commonly you'll see the term fuselage station number. Okay, we know the weight of an item, we know the location of it, the arm, the distance after the datum. If you multiply the weight times the arm, what you get is the moment. And the moment basically is the leverage effect, is the force applied at that particular location. And the force applied at a particular location in the aircraft depends on what the weight is that's located there and what the distance, what the arm is of that item from the datum point. And if you're given any two of these items, weight, arm, or moment, you can always find out what the other number is. Weight times arm equals moment, but you can take the moment and divide it by either the weight or the arm in order to get the other information. For example, the FAA may say to you on your mechanics test, you've got a 40-pound generator and it's applying plus 1,400 inch-pounds. It's applying a moment of 1,400 to the reference axis. Where is the generator located in the aircraft? Okay, what we have in this particular case is we have the weight and we have the moment. Weight times arm equals moment, so all you have to do is turn that around and take the moment and divide it by the weight, and that will give you the arm. The arm is the location in the aircraft. So the moment was 1,400 inch-pounds, that's the moment. The weight of it was 40 pounds. 1,400 divided by 40 pounds gives you a location of plus 35 inches. Now, if all of the arms are positive, and if you're adding a weight or a weight is there as opposed to a weight being taken away, if all of the numbers you're working with are positive, the answer will be a positive also, so that is a plus 35 inches. It's not a minus 35 inches. Now let's talk some more about the center of gravity in the aircraft. The center of gravity in an aircraft is a point where the nose-heavy and tail-heavy moments are exactly equal. The forces on to the aft of the center of gravity are exactly balanced by the forces to the forward of the center of gravity. The airplane is perfectly level. If an aircraft were suspended from this point, from the center of gravity point, it would remain level. It would not tilt nose down, it would not tilt tail down, it would stay perfectly level because the center of gravity is the balance point on the aircraft. When you're computing weight and balance, an airplane is considered to be in balance when the average moment arm of the loaded aircraft, in other words, when the average location of all the weights in the aircraft, including the aircraft itself, falls within the center of gravity range. There will be an allowable range within which that center of gravity can move, and as long as it's within that, it is considered to be in balance. Considered to be in balance. And we're going to talk about figuring out where the center of gravity is and what to do about it if it's not within the allowable center of gravity range. Now, what if you load an aircraft and calculate the weight and balance and then decide that an item you loaded in the baggage compartment wasn't needed? You know the baggage compartment is located aft of the center of gravity of the airplane. With all other things being equal, removing an item of useful load that is located aft of the center of gravity will move the CG forward in proportion to both its weight and its location in the aircraft. And that makes sense. You know that this airplane will balance at the CG, and if you make it lighter behind the CG, the balance point or center of gravity will have to move forward. Now, when we talk about the location of the center of gravity and its allowable range in small airplanes, we usually base that solely on the distance from the datum or datum line. And you may have noticed that the center of gravity seems to fall somewhere about 25% of the chord of the wing. In other words, about 1/4 of the distance back between the wing's leading edge and the wing's trailing edge. Pilots and flight engineers of large airline-sized jets find it more meaningful to know where the center of gravity is in relation to the chord of the wing, not the datum, because it gives them more information about what the handling characteristics of the aircraft will be. The problem is that large jet airliners have swept, tapered wings. So what do you use for the chord as a reference for the center of gravity? Do you measure it from the leading edge at the root next to the fuselage, or from the tip way out here? As you can see, there's a big difference in the chord length depending on where you measure it. Well, the engineers solved this problem by taking an airplane's swept wing shape and creating an equivalent, more rectangular airfoil shape. And then they calculate a mean or average aerodynamic chord, which we call MAC, M-A-C, mean aerodynamic chord. And as you can see, this is what the mean aerodynamic chord would look like on this particular wing. It's the chord located somewhere near the middle of the wing. Okay, now that you have a chord to work with, you need to know where the MAC starts in relation to the datum. In other words, you need the location of the leading edge of the mean aerodynamic chord, shortened to LEMAC, and you also need the location of the trailing edge of the mean aerodynamic chord, called TMAC. So for swept wing aircraft like this, you'll see a LEMAC and a TMAC, and they're defined by their distance from the datum. Now, when you find the center of gravity as the distance from the datum, you can also say what it is in terms of a percentage of the mean aerodynamic chord, or MAC, and that's exactly what they do with jet transport airplanes. Just as you measure arms aft from the datum, you measure the CG in distance aft from the LEMAC, and then you express it in percent of MAC. So if you know that the center of gravity is at 24% of MAC, then you also know that the center of gravity is located at a point equal to 24% of the length of MAC measured from the LEMAC. Now let's assume you're going to have to weigh an aircraft. Here a mechanic is jacking up an airplane to be able to get scales under the wheels. Maybe the weight and balance documents have been lost. Or maybe you're working with an airplane that's used commercially and you're going to have to actually weigh it in order to know for sure what the weight really is. First of all, you're going to have to level the aircraft. If you're going to have useful information for determining the center of gravity, when you weigh the aircraft, you need to weigh it in a level flight attitude. So, how do you know when an aircraft is level for weighing? You go to the type certificate data sheet to get information and specific instructions for that type of aircraft. Now, some aircraft call for putting a spirit level on a designated structural member or resting it on screws threaded into specific locations. A spirit level is just like a carpenter's level. It has a fluid-filled tube with a bubble in it. In some large aircraft, permanently attached spirit levels are located in an equipment compartment or in a wheel well. And this can give an accuracy as great as 1/8 degree. Another method is to use a plumb bob that you suspend from a designated point, such as inside the aircraft. It has a target on the floor, and when the plumb bob is directly over the target, the aircraft is level. So the FAA may ask you which method, a plumb bob and grid plate, an inclinometer, or spirit levels, generally yields the highest degree of aircraft leveling accuracy. Well, the highest degree of accuracy is found when using spirit levels. Now, why might you need to reweigh an aircraft? Well, one reason would be if the weight and balance records of the aircraft are lost or for some reason become inaccurate. Maybe they don't correctly reflect equipment that's been added or taken out of the aircraft, or perhaps modifications that have been done to it. And if the weight and balance records are lost or inaccurate, then the only way that the correct empty weight for that aircraft can be determined is by re-weighing the aircraft. You cannot look in the flight manual or the pilot's operating handbook, because that will give the weight and balance information for a typical aircraft, but that's certainly going to be different than the information for that specific airplane. Now, before you weigh an aircraft to determine the empty weight of it, you've got to take some things out of it. Remove everything from the aircraft except the items that are on the aircraft equipment list. You also want to drain all of the fuel that you can get out of it. There will be some unusable fuel left in it. And you want to fill the hydraulic reservoir if it has a hydraulic system in the aircraft. If it has any water reservoirs, you drain the water reservoirs. And if you've got a bathroom on board, you drain the lavatory tanks. But as far as the items in the aircraft, you want to get rid of everything except the ones that are on the aircraft equipment list. If people have got briefcases and all kinds of clipboards and stuff like that, all of that stuff has got to come out, because it will come out from time to time, and you only want, when you're figuring the empty weight, the stuff that's going to be staying in the airplane. Okay, when you go to find the empty weight and weigh the aircraft, the weighing points that you use, you have to indicate exactly what weighing points you used on the aircraft weighing form, because the arm values, the distances from the datum point that you are using here when you weigh it, the arm values used in the computations are based on the locations of the weighing points. So you've got to put them down on the form. Now, after locating the weighing points, when you're measuring the arms from the datum, you want to make sure that you're measuring parallel to the center line of the airplane. You do not want to introduce error by having your tape at an angle. So if you're weighing an airplane to obtain the CG, always extend the arms from the weighing points parallel to the center line of the airplane. Now, the empty weight of an aircraft is determined by subtracting the tare weight, T-A-R-E, tare weight, from the scale reading. The tare weight consists of things like chocks or supports to hold the tail up, in this case, to get a level flight attitude. Anything that sits on the scale, and therefore the scale is reading the weight of it, but is not part of the airplane. Chocks to keep the airplane from rolling off of the scales, supports to hold the plane in the proper level flight attitude, those would be considered tare weight, and you subtract those from the scale reading, because what you're after is the net weight of just the aircraft itself. And then you add the weights at each weighing point. In this case, we've got 3 weighing points. We've got a left main gear, a right main gear, and we've got the tail gear, and we're weighing the airplane at each of those points. So we would take the scale readings, subtract the tare weights, which are the chocks and the tail support, and then we would add those 3 net readings together in order to get the empty weight of the aircraft. Okay, the FAA will give you a number of problems working with the empty weight in the center of gravity, so let's talk about one of them. First of all, they'll say to you that you're going to be weighing this particular aircraft. Now, they'll give you all kinds of different aircraft, and they will not tell you exactly what airplane you're working with, but it doesn't really matter, because it's just a process of going through the numbers. What they will say to you is that when you weigh the aircraft, the net combined weight at the main gears is 3,540 pounds. And the arm of the main gears is 195.5 inches, which means that from the datum line on the airplane to the main gears is 195.5 inches. That's the arm, the distance the main gears are behind the datum line. Okay, they say that the net weight at the nose gear is 2,322 pounds, and that the arm of the nose gear is 83.5 83.5 inches, meaning that it's 83.5 inches behind aft of the datum line. And they tell you that the datum line is forward of the nose of the aircraft. That makes everything easy. We don't have to worry about exactly where it is. All we know is that these are all going to be plus numbers, and it's going to be easy to work with. Now, in order to figure out the center of gravity, what we want to do is work with the formula weight times arm equals moment. And the first thing we do with that formula is we set up a table like this with 4 columns in it. In the left column, we list the weight points that we're working with, which are the various gears. Then we list the weights at each location. Then we list the arms there, the distance aft of the datum line, and then we put the moments in. Weight times arm equals moment. They gave us the weights, they gave us the arms, we multiply in order to get the moment. Now the first thing we know is the weight at the main gears, and the weight at the main gears was 3,540 pounds. The arm, we were told, was 195.5 inches. Let me be your calculator for you, and 3,540 pounds times 195.5 inches gives us a moment of 692,070. The moment is the force exerted in that particular location. The next thing we list is the nose gear. The nose gear, the weight was 2,322 pounds at an arm of 83.5 inches. Weight times arm equals moment, and the moment for the nose gear is 193,887. Now, the next thing we do is total the weights and total the moments. You don't total the arms. There's no such thing as a total arm. There is an average arm, which is the same as the center of gravity, but there's no such thing as a total arm. So when you total the weights, the total weights come up to 5,862 pounds. When you total the moments, the total moments come up to 885,957. What we really want, though, is the center of gravity. To get the center of gravity, if you know the moment and you know the weight, all you have to do is divide. Total moment divided by total weight will give you the average arm or the center of gravity. The total moments were 885,957. The total weight was 5,862 pounds. And when you divide that, the center of gravity, the average arm, is 151.1 inches. 151.1 inches is the center of gravity, or the average arm, the average location of the weight, if you will, on the aircraft. Okay, the FAA will give you another question, and they will ask you to determine the empty weight center of gravity, but they put some extra stuff on board the aircraft, some of which should be there and some of which has to be subtracted in order to get the empty weight and the center of gravity of the aircraft. Okay, what they say is, here you've got an aircraft. The datum is forward of the main gear. The distance from the tail gear to the main gear is 360.26 inches. The distance from the datum line to the main gear is 30.24 inches. On the right main gear, we have weight on the scale of 9,980 pounds. On the left main gear, we've got a weight on it of 9,770 pounds on that scale. And on the scale at the tail, we're showing a weight of 1,970 pounds. Now, as we look at this diagram, what they have given us is the distance from the datum line to the main gear, and then from the main gear back to the tail. And in order to get the datum to the main gear, the datum to the tail, what we're going to have to do is add the distance from the datum to the main gear to the distance from the main gear back to the tail gear. And so we're going to have to add the 360.26 and add to that the 30.24, and that will give the distance all the way from the datum line back to the tail gear on the aircraft. And that comes up to 390.5 390.5, and we're going to plug that into our table in a little bit. But the FAA also says we've got some additional items in the aircraft when we weight it. And what those items are, first of all, is a lavatory water tank. We've got the lavatory water tank, and the weight in that tank is 34 pounds, and the location of the tank is plus 352, and that means 352 inches aft of the datum line. We also have hydraulic fluid. There are 22 pounds of hydraulic fluid, and it's located at -8. That means that it is in front of the datum line. It is located at -8 inches. We also have some removable ballast in the aircraft. It can be put in or taken out. It's removable, not fixed, and that is 146 pounds, and that's located at plus 380. So that's 380 inches aft of the datum line where the removable ballast is located. Now, when you're working a weight and balance question, the result of a weight being added or removed and its location relative to the datum line determines whether the moment is going to have a plus or a minus sign in front of it. For instance, if a balance computation requires that an item which is located aft of datum be removed, in that case you've got a minus weight because you're getting rid of the weight, but you have a plus arm because the item is aft of the datum, and that makes it a positive number. When you multiply a minus number by a plus number, you're going to get a minus number. So if you're removing a weight, the weight would be entered as a minus. At the arm after the datum would be a plus arm, but the result of multiplying those would be a minus moment, because just like you're getting rid of the weight out of the aircraft, if you remove an item, you are also getting rid of the leverage effect of it, which is what the moment is, and therefore you would have a minus moment when you go through the calculations. So let's set up our table again. Weight point or item, weight, arm, and moment. Weight times arm will give us the moment. Okay, the first weight point is the right gear, and on the right gear we had a weight of 9,980 pounds. The arm they gave us was 30.24 inches, and when you multiply, the moment is 301,795.2. The second item is the left gear. The weight they gave us on the left gear was 9,770 pounds. The arm is the same as for the right gear. They're the same distance aft of datum, 30.24. Multiply weight times arm, and the moment is 295,444.8. Then we've got the tail gear. The tail gear, we were told the weight there is 1,970 pounds. The arm of the tail gear is 390.50 because we took the distance from the datum line to the main gear and then the distance from the main gear back to the tail and added them together to get that 390.50. Multiply, and the moment is 769,285. Now, as far as the hydraulic fluid is concerned, hydraulic fluid belongs in the airplane. It is part of the empty weight. So we don't do anything at all as far as the hydraulic fluid is concerned. It was included when the airplane was weighed. It should be included when the airplane is weighed. But what we do have to remove is the lavatory water. We got to get rid of that H2O, the lavatory water, because it doesn't belong. There was 34 pounds of it, and we're getting rid of it. So under weight, we put a minus 34. The location of the lavatory water tank is 352 inches aft of datum. It's aft of datum, so it's a positive number. We put it in there as 352. Weight times arm equals moment. We get a moment of a minus 11,968, and it's a minus moment for the lavatory water because we're getting rid of the weight, and when you get rid of the weight, you get rid of the effect of that weight, and that's what the moment is. We also have to get rid of the removable ballast. Because it is removable, it's not included in the empty weight of the aircraft, and therefore we put in a minus 146 pounds. pounds for the removable ballast. The arm of it is 380 inches. Weight times arm equals moment. The moment for the removable ballast is a minus 55,480. And then what we do is we total the weights and we total the moments. The total weights are 21,540 pounds. The total moments are 1,299,077 for the moments. Okay, we've got the weight and we've got the moment, but what we really want to have is the center of gravity. Center of gravity, take the total moment, divide it by the total weight, and that gives you the average location of the weight, the average arm or center of gravity. And when you divide the total moment by the total weight, you get a center of gravity in this particular case of 60.31 inches. 60.31 inches. Remember, hydraulic fluid belongs in the airplane. Do not get rid of it. But water in a lavatory tank or removable ballast are not part of the empty weight and do have to be subtracted out. Okay, they'll give you another question that looks like this. They'll say to you, you've got an airplane, and rather than giving you the weights on each of the wheels, they'll say to you that the total empty weight as weighed is 5,862 pounds, and the total moment of the airplane with the empty weight is 885,957. On board the aircraft, when it was weighed, are a couple of additional items. First of all, alcohol. 20 pounds of alcohol at a location of plus 84 inches. Also hydraulic fluid. On the hydraulic fluid, you had 23 pounds on board at a location of plus 101 inches. The pluses simply mean that it's located after the datum line as opposed to in front of it. And the question is, what is the center of gravity, the empty weight center of gravity of the aircraft? So we set up the table. The weight point or items, the weight, the arm, the moment. Weight times arm equals moment. And the first thing we put in there is the empty weight of the aircraft itself. The weight is 5,862 pounds. The moment is 885,957. And the arm of the airplane at that point is 151.14. Now, the arm was not given to us. The arm we calculated because if you have the moment and you have the weight, you can divide and you can come up with the arm. And we did it just to fill in the table. Okay, alcohol. Is alcohol included in the empty weight of the aircraft? No, it's not. So the alcohol has to come off. There were 20 pounds of it, so under weight you put a minus 20. It was located at 84 inches, so under arm you put 84. Weight times arm equals moment, and you get a minus 1,680 for the moment. You're removing the alcohol, so you remove both the weight of the alcohol and also the influence, the effect of it, the moment of it, from the calculations. Now, hydraulic fluid. Does hydraulic fluid belong in the empty weight? Yes, it does, and therefore you don't do anything about it. It was in there when the aircraft was weighed. It's supposed to be in there in the empty weight, so you don't have to worry about doing anything with the hydraulic fluid. The next thing you do is you total the weight and you total the moment. The total weight is 5,842. The total moment is 884,277. And what we want to know is the empty weight center of gravity. So we take our formula. Total moment divided by total weight will give us the center of gravity, and you take the total moment, 884,277, divide it by the total weight, 5,842, and you get a new center of gravity for the empty weight of 151.365 inches. 151.365 inches. See? Nothing to it. And really there isn't, as long as you remember to set up the table, because it's important to keep the problem organized. Otherwise you end up with numbers all over your scratch paper and you don't really remember after a while exactly what the numbers mean. Here, the FAA will give you another question having to do with determining the empty weight after an engine change. And they'll say to you that you've got an aircraft where you took out a B model engine that weighed 175 pounds and you installed instead a D model engine that weighed 185 pounds. The datum line is located right about here, roughly in this diagram, the leading edge of the wing, because of the way the numbers, the stations, are given to you. They say to you that the station of the engine is a minus 62 inches. Well, if it's a minus number, it has to be in front of the datum line, which means the datum line needs to be about the leading edge of the wing and the engine's out in front of it. And they also tell you that the previous empty weight center of gravity is 13.48 inches and that the previous empty weight, this is before the engine change, was 998 pounds, and what they want to know is what is the new empty weight center of gravity when you get done with this engine change. So you set up the table, item, weight, arm, and moment, and then start filling in the numbers. And the first thing is the original empty weight of the aircraft. It weighed 998 pounds. The arm was 13.48 inches. Weight times arm equals moment, and the original moment was 13,453.04. Now you're going to take out the B model engine. So under weight you put a minus 175 pounds because you're getting rid of it. Now the arm of that B model engine was a minus 62 inches. That minus is because it's in front of the datum line. And that's fine, no problem. Put it in as a minus arm. But the thing that happens is when you multiply a minus weight times a minus arm, this time, instead of getting a minus moment, you get a plus moment. And you get a plus moment of 10,850 because a minus number multiplied by a minus number will give you a positive number. Okay, you took the B model engine out. Now you put the D model engine in. You install the D model engine. It weighs 185 pounds, so you put under weight a plus 185. The location of it is an arm of minus 62 inches, so under arm you put a minus 62. Weight times arm equals moment, and you get a moment of 11,470, and that is a minus moment because you had a minus arm. In this case, it's not a minus weight that makes it a minus moment, but the arm has a minus number and a negative number, and therefore you end up with a negative number for the moment. And then you simply total the weight and total the moment. The total weight is 1,008 pounds. The total moment is 12,833.04. And in order to get the new center of gravity, we simply use our formula of dividing the total moment by the total weight to get the center of gravity. And when you divide the total moment, 12,833.04, by the weight of 1,008 pounds, the new center of gravity for the empty aircraft after the engine change is 12.73 inches. 12.73 inches. Okay, the FAA will ask you another question where they don't change the engine, but they do a lot of other changes on the aircraft. And what they say is the original empty weight is 2,886 pounds. The original moment of the empty aircraft is 101,673.78. What you do is you take two passenger seats out. The passenger seats weigh 15 pounds each, and they're located at plus 71. That means 71 inches aft of datum. You install a cabinet that weighs 97 pounds that's located at 71 inches. You install a seat and a safety belt that weighs 20 pounds, and you put it in at 71 inches. And you install radio equipment, and that radio equipment weighs 30 pounds, and it's located at 94 inches. And the question is, what is the new empty weight center of gravity? Okay, so you simply set up the table, item, weight, arm, and moment. And the empty weight of the aircraft is 2,886 pounds. The moment was given as 101,673.78. To get the original arm, the center of gravity, you divide. If you've got the weight and you've got the moment, you divide the moment by the weight, and you get the arm on the empty weight of the aircraft. And it was 35.23 inches to begin with. Okay, you take out 2 seats. The 2 seats weighed 15 pounds each, but that's a total of 2 times 15, or 30 pounds you're getting rid of, and it's a minus weight because you're taking it out of the aircraft. It's located at 71 inches. Minus 30 times plus 71 gives you a minus moment of 2,130 for the seats you removed from the aircraft. Now you install a cabinet. The cabinet weighs 97 pounds, so under weight you put 97 pounds, under arm you put 71 inches. Weight times arm equals moment, and the moment for the cabinet you installed is 6,887. You also installed a seat at the same location, but this seat weighed 20 pounds, not 15. 20 pounds under weight times 71 inches under arm gives you a moment for the seat you installed of 1,420. You also put in a radio, 30 pounds worth of radio at location 94. Weight times arm gives you a moment of plus 2,820 for the arm on the radio that you put in. And then you total the weights and the moments. The total weights come up to 3,003 pounds. The total moments come up to 110,670.78. Okay, what we want to do now is we want to determine the center of gravity. We want to figure out where the center of gravity is located. Total moment divided by total weight will give us the center of gravity. 110,670.78 divided by 3,003 gives the new center of gravity of 36.85 inches. Now, most of the problems like this will stop right there, but not all of them will. In some cases, the FAA will say, what is the change from the old center of gravity? How much has the center of gravity moved, and which direction has it moved? The new center of gravity is 36.85 inches. The old center of gravity was 35.23 inches. When you subtract the two, the difference, the change, is 1.62 inches. 1.62 inches. Now, the new center of gravity is further aft of datum than the old one is because it's a bigger number. It's 36 inches and some instead of 35 and some. So the center of gravity has moved rearward. It's moved towards the aft position in the aircraft when you made the change. So the new center of gravity is 1.62 inches aft of the old center of gravity. Now let's talk about the theory of weight and balance. The theory of weight and balance is the same theory as of a lever that is in balance, in equilibrium, when it's resting on a fulcrum in a level position. This, in essence, is what we want the airplane to do. The concept we're working with on the airplane, the center of gravity is the same as the fulcrum. It's the balance point here on our lever. Now, let's talk about the concept of lever arm. The distance that any object is from that fulcrum is called the lever arm. What we've been working with in general has been just the arm, the distance that something is from the datum line, and the datum line has been up at the nose of the airplane. But let's assume that you put a fulcrum at the center of gravity of the aircraft and then measured from that instead of measuring from the datum line. What you would have then is a lever arm, because this is the distance behind the balance point, or in front of the balance point, the point that the aircraft or this lever is rotating about. Center of gravity is what the aircraft rotates about, and so if you measure from there instead of from the datum line, you get the lever arm of a particular item. And the FAA will give you some questions that require you to work with that. For instance, they will say to you that you have put 2 boxes in an airplane. We're going to use this lever to illustrate it because it works a little bit better. One of the boxes weighs 10 pounds and is located 4 feet aft of the center of gravity. Another box weighs 5 pounds and is located 2 feet aft of the center of gravity. You've got another box. You've got a 20-pound box, and you're going to put it in front of the center of gravity. And the issue is how far forward of the center of gravity, the balance point, the fulcrum, if you will, how far forward of the center of gravity can that 20-pound box be placed so that the center of gravity does not change. In other words, you started off with a lever in balance, an airplane in balance. You added 2 boxes behind the center of gravity. You're going to put a third one in front of it, and the issue is how far forward of the center of gravity does that box need to be in order to balance these other 2 weights. Okay, simply set up a table. And in this particular case, when you set up the table, the columns are item, weight, lever arm, and moment. Lever arm, because we're not measuring from the datum line, we don't even know where that is in this particular problem. What we're doing is we're measuring from the center of gravity, which is the same as that fulcrum that we looked at. Okay, so we start adding the items in. And first of all, we've got box 1, which weighed 10 pounds, had a lever arm of 4 feet, and 10 times 4 gives us a moment of 40. Then we add in box 2, which weighed 5 pounds, had a lever arm of 2 feet, and that gives us a moment of 10. And then you total the moments. We're not really interested in the weights here. All we're interested in how much force do we have to counterbalance. And the total moments added aft, to the aft of the CG, to the aft of the fulcrum, are moments of 50. Now, in order for this aircraft to be in balance, when we put the third box in, what we have to do is we have to balance those moments. So we're going to have minus 50 moments. That means an effect of 50 forward of the center of gravity. We know we're going to put 20 pounds forward. What we don't know is how far forward we have to put it. Well, remember that weight times arm equals moment, and moment divided by weight will give you the arm. It's the center of gravity if you're working with a whole airplane, or the arm if you're working with an individual item. And so we have a moment of 50, we have a weight of 20, and when we divide 50 by 20, we have to put that box 2.5 feet forward of the center of gravity. It's 2.5 feet forward in order for that aircraft to be in balance when that third box goes into it. Now, the FAA will ask you a question about putting a ballast weight in an aircraft to bring the center of gravity within the center of gravity range. We've already said that there's a certain allowable movement on the center of gravity that it's allowed to move within, and you can't exceed that safely. The FAA will give you the following information. They'll say you've got a loaded aircraft that weighs 4,954 pounds. They'll tell you that as currently loaded, the center of gravity on the aircraft is located at 30.5 inches, 30.5 inches aft of the datum line. They'll tell you that the allowable CG range on the aircraft is 32 inches to 42.1 inches. You can see already that you've got a problem, because the center of gravity as the aircraft is loaded is forward of the allowable center of gravity range. It's outside the range to the forward of the aircraft. Now, to get the center of gravity back in range, what you're going to do is put some ballast in the back of the aircraft, and the arm on the ballast is 162 inches, which means 162 inches aft of the datum line. What they're going to say to you is, after giving you these numbers, how much weight of ballast do you put at this location in order to move the center of gravity within the allowable range? And that means that you need to have the center of gravity move from 30.5 inches to exactly 32 inches, because when they ask you what is the minimum weight that you have to put in the ballast location, what they're asking is what is the minimum weight needed to bring the CG to where it's exactly legal. Not in the center of the range, but to where it's exactly legal, and exactly legal would be a position of 32 inches. Now, The way that you think about this is that the weight, the ballast that's added, causes a moment change in the whole aircraft that's equal to the moment change caused by adding the weight. So what you do is you put a fulcrum where you want the airplane to be in balance when you're done. You put it where you want the airplane to be in balance when you're done, which in this case is the forward limit of the allowable center of gravity range. And from that fulcrum, you compute lever arms for the items that we're working with. The center of gravity is 30.5 inches aft of datum. The forward limit of the center of gravity range is 32 inches aft of datum. From 32 to 30.5, the difference between those is 1.5 inches. So we've got a lever arm here of 1.5 inches that we have to move the center of gravity. Now, from where we want the airplane to be in balance when we're done, which is 32 inches, back to the location of the ballast that we're going to put in the plane is a distance of 130 inches. And we get that by taking the arm of the ballast, which is 162 inches aft of the datum line, and subtracting from 162 inches the forward location of the foremost limit of the center of gravity, which is 32 inches. 162 minus 32 gives you a lever arm of 130 inches for the ballast weight that we're going to put in there. And then all we have to do is work through our same table, but using the lever arm rather than the original arm, the distance from the datum line. So when we put in our table, first of all, we put the CG shift that's needed. The weight of the aircraft is 4,954 pounds. That goes under weight. The lever arm is a minus 1.5 inches because the original center of gravity is 1.5 inches in front of where it's allowed to be. Weight times lever arm gives us the moment, and that gives us a minus moment of 7,431. What we've got here is we've got moments of 7,431 in front of the allowable CG limit that we have to counteract, that we have to counterbalance. So to balance those moments, we need positive moments of the same amount, 7,431. Okay, we've got the positive moments of 7,431 that we need. We know that the lever arm on the ballast is 130 inches. And all we have to do then is divide. This time we're dividing in order to come up with the weight. And here's what it's going to look for. We take the moment, which is 7,431, and we divide it by the arm. The lever arm was 130 inches, and the ballast weight we have to come up with then, have to put in the aircraft, is 57.16 pounds. 57.16 pounds. Remember we said if you've got any two numbers, you can always get the third in our weight and balance formula of weight times arm equals moment. In this case, we got the moment in the arm, and it's the weight we need to find out, and we need 57.16 pounds of ballast in order to bring the center of gravity back to the leading edge, to the forward limit of the allowable center of gravity range. Now let's talk some more about that center of gravity range, that empty weight center of gravity range. The empty weight center of gravity range is the allowable range of travel within the center of gravity limits. If the empty weight CG of an airplane falls within these limits, then it is not necessary to calculate extremes on the center of gravity, because as long as the empty weight CG of an airplane falls within the empty weight CG range, it's not possible to load the aircraft so that it's going to get out of the CG limits as long as standard loading arrangements are used. But there are some aircraft where the empty weight center of gravity is outside the center of gravity limits, empty weight center of gravity limits, and you have to calculate center of gravity extremes to see whether or not that plane is going to be within center of gravity when it actually is flown with people and so on in the aircraft. And when you do that, you may end up with a situation where you have to put some ballast into the aircraft. So they're going to ask you about the weight and balance extreme conditions and what kind of figuring you do. Well, first of all, let's assume that you're going to calculate the maximum forward center of gravity. If you're doing a forward center of gravity check, what you want to know is the aircraft going to be out of the center of gravity limits, the loaded center of gravity limits, to the fore? And in order to get the extreme condition on that, what you do is everything that's located aft of the datum line, you take the FAA designated minimums for. You take the minimum weights, minimum arms and moments of any items that are located aft of to the rear of the forward center of gravity limit in order to run a loaded forward center of gravity check. Because what you want to see is if the things that are located behind this forward limit are at their very minimum values, will the center of gravity of the aircraft be out of the limits forward, or will it still be within limits? Then you make a rearward loaded center of gravity check. Now, if you're doing a rearward loaded center of gravity check, what you want to do is you want to take for your values the minimum weights, arms, and moments of anything that is located forward of the rearward CG limit. Because on a rearward check, what you're trying to figure out is anything that is located in front of the rearward limit, if it's at its minimum value, will the aircraft end up out of center of gravity to the rear in the loaded condition as opposed to the empty weight condition. And these extreme checks sometimes have to be done depending on where the empty weight center of gravity falls. Now, if you're doing adverse loading checks like these, under what condition would you do them? Well, if you're conducting an adverse loading check, you want to make sure that you're using a load that is at or below the maximum gross weight of the aircraft. It makes no sense to do adverse loading checks using loads that exceed the aircraft's maximum gross weight. You'd learn nothing about the extreme forward or rearward loaded CG if the aircraft is not within the maximum gross weight limit. Now, the FAA may ask you, would you do an adverse loading check anytime a repair or alteration causes EWCG, empty weight CG, to fall within the empty weight CG range? No, you wouldn't. Remember earlier we said that as long as the empty weight CG of an airplane falls within the empty weight CG range, it is not possible to load the aircraft so that it's going to get out of the CG limits, as long as standard loading arrangements are used. So if a repair or alteration causes the empty weight CG to fall within the EWCG range, you do not need to do the adverse loading checks. Now, on the other hand, you might get asked if you should conduct an adverse loading check at specified flight hour or calendar time intervals. There is no flight hour or calendar time interval requirement for an adverse loading check. You will only need to do an adverse loading check after you make a repair or alteration that causes the empty weight CG to fall outside the empty weight CG range. And you will conduct the adverse loading check under conditions where the aircraft is at or below the maximum gross weight. Let's talk about helicopter weight and balance. First of all, with helicopter weight and balance, you basically compute it the same as a fixed-wing aircraft. But the difference is that the center of gravity range is more restricted than it is for airplanes. In helicopters, the center of gravity range is going to be more restricted than it is in airplanes. The loading is very critical in a helicopter because improper loading that has you exceed either the fore or the aft center of gravity limits could cause the reduction or loss of effective cyclic pitch control. Now, the cyclic tilts the plane of the rotor in the plane of the main rotor in the direction of desired horizontal movement. And if you get the center of gravity out either fore or aft limits, what you can do is reduce the effect of that cyclic pitch control or even lose it, and that gives you very substantial control problems in the helicopter. And that is what you need to know about weight and balance.